what you'll notice from my general eigenvalue expression is I have A, V, lambda, and V. So if I know that my eigenvalues are related to my frequencies, that takes care of lambda, and my eigenvectors are related to my mode shapes, that takes care of V. So what am I left with? I'm left with A. So I need to get all of the information of my multiple degree of freedom system into A, but A is a single matrix, and I have two matrices, right? I have mass and stiffness. So we want to generate a mass normalized stiffness matrix. So we need, going to go on an adventure here. We need to find the mass normalized stiffness matrix. We'll call that K tilde. Not as exciting as Indiana Jones looking for the Temple of Doom, but we're going to get it by the end. All right, not every joke's a winner. Not every joke's a winner. Okay. The next thing, anyone remember Cholesky decomposition? All right, so Cholesky decomposition, French guy. If you have a real positive definite matrix let's do that in blue. So a Cholesky decomposition. That just means that, and we'll keep it in blue, that A, which is our real positive definite matrix A, can be expressed as L transpose, where L is the lower triangle of A. Is lower triangle of A, right? And so a matrix is positive definite if, well, a matrix is positive definite if X transpose AX is greater than 0, where X is any non-zero vector, right? So you have any numbers, if I take the transpose of it times A multiplied by the same vector that I had before, if I end up with 0, then I have a positive definite matrix, all right? All of that's great. How do we get the lower left-hand triangle, right? That's the question that's being asked. So Cholesky decomposition, for our case, we're just going to define it as, so actually we're going to define it two ways. A little tricky, but it's important because the literature kind of is split on this one. So it's just important to know that they're both true. So L, how I like it, but a lot of people go m to the 1/2, also very correct, is equal to your mass matrix M1, and if it's to the 1/2, it's just going to be the square root, right? Typically a mass matrix is going to be diagonal, so we're just going to fill in our diagonals, and we have the square root of M2. All right. This is not always true, but it's true for every example in the book. That makes sense? So you go out and you get a job doing finite element analysis. Sometimes you're going to have to go back and check this, right? But this is true for every example in the book. So for the special case where we have diagonal matrices, every example in this class, every example in undergraduate education, I bet. So for the special case of diagonal matrices, M is equal to M1 half M1 half, which is quite useful, right? So that's quite useful. We can rebuild our M. The inverse of the diagonal, right? Well, that's just going to be L to the negative 1, which is equal to M to the negative 1 half, which is just equal to 1 over the square root of M1, 0, 0, 1 over the square root of M2. So that gives us a lower left-hand matrix, right? So so now that we have a little bit of mathematical background, we're going to pull from these in a little bit, right? It's like cooking. We made things on the side, and we're gonna throw them in a little bit. So let's restart our solution here in terms of our equation of motion, right? It's a very good place to start. So again, our starting back at the equation of motion, and for simplicity, we have drop damping from all of this, right? So we have mx vector double dot plus kx vector is equal to 0. So that expression can be transformed into a symmetric eigenvalue problem, which is what we want, right? Because if we have a symmetric eigenvalue problem, we can leverage the strengths of symmetric eigenvalues and the mathematics behind that that have been deployed on computer solvers, right? So to do that, let's set x bar is equal to m to the negative 1 half q vector, and multiply the equation of motion by m to the negative 1 half. Oh, maybe put that one word, right? So we have two things we want to do that. We have two things we want to do to this expression. Maybe we'll make that all orange if I can grab it. There we go. We have two things we want to do to that expression. So if I do both of those into my equation of motion, I am going to end up with m to the negative 1 half, m, which I had before, and then x bar is going to become here. Let me. So that's from multiplying. Purple is what I had. Orange comes from m to the negative 1 half q vector, double dot, right? Because it's my acceleration term. Plus, oh, that got messed up. That's got to be blue. No, there we go. Plus back to blue, m to the negative 1/2, and then I already had a k in there, and then m to the negative 1/2 q vector is equal to 0. Luckily, if we just look at this, m to the negative 1/2 m to the negative 1/2 is going to be my identity matrix. Right? So I like identity matrices because I like doing math with ones. Right? When you do math with ones, things tend to get very simple. And so now I'm left with this other expression. I'm going to give that one a green check mark. That one's been taken care of. I'm left with this other expression, m to the negative 1/2 k m to the negative 1/2. Now what does that equal to? I'm going to define that as my mass normalized stiffness matrix, k tilde. So we found it. And the value of this is that's one matrix that has information from my mass and my stiffness, right? So now I have a single mass normalized stiffness matrix, k tilde, that I can use to solve that out. That gives me an expression in my equation of motion. Equation of motion becomes my identity matrix q vector for acceleration. That's my participation factor, right? Remember that? Remember that q is my participation factor of my modes. But that's not super important right now. K tilde q vector is equal to 0. All right, so now I have a mass normalized equation of motion, right? So if you think about taking the like the standard form of an equation of motion without damping, right? This is equivalent to that because we don't have any damping in the system. All right, now we have to solve this. How do we solve these equation of motions? Want to take a stab at it? Anyone? What? Oh, like force equals ma? Yeah, so how do we, let me maybe rephrase that. Yes, that's part of it. How do we solve an equation, how do we solve an ODE? What's the solution we can use to solve an ODE?
Separation by variables.
We can separate by variables, we can, what's the easy one that we've been doing?
Make a guess.
We've been making a guess. We've been assuming a solution. What if we assume the same solution that we've assumed all the other times? Or do you want to assume something different this time? Yeah, perfect, right? So let's do that with a slight variation. We're going to assume a solution. Brings us back to our good friend Euler. We're just going to say, hey, I bet I can get q vector equal to my eigenvectors. Well, let's just say E right now. Sorry, V, e to the j omega t. Did that look familiar? And the little bars on top of the V are to try to express the idea that it's bold. So let's just toss that back into the equation of motion, right? Let's not think about it too much. Just take the derivative again, toss it back to the equation of motion. I get negative V omega squared e to the j omega t.
Is that V through delta?
V.
Okay.
Plus a delta is like that, right?
V gradient.
Oh.
Gradient,
Plus equivalent stiffness matrix V e to the j omega t equals 0. Yeah. So identity matrix is 1, 1, 1, 0, 0, 0. Those are zeros, not sixes. All right, so let's say we can drive out the non-zero scalar e to the j omega t, right? That's just going to shift it up or down. You can divide that by 0. It's not a huge part of the problem right now. And so we can get K mass normalized stiffness matrix V is equal to omega squared V. Right? So our V is our eigenvectors, right? Or a matrix of our V is a matrix of our eigenvectors, and the eigenvectors are related to our mode shapes. What would happen if we had a matrix of mode shapes that were all 0? Pretty useless. Trivial, right? Absolutely not helpful. So we're going to say, all right, V can't equal to 0. We're just going to make that assumption. So with that, we can relate or rewrite this just a bit as a general eigenvalue problem, which is right. So instead of A, we're going to have K tilde. We're going to have our matrix of eigenvectors is equal to lambda matrix of eigenvectors. Right? Now, if I look at this one more time, I say, okay, well, just lambda is equal to omega squared. Or omega is equal to the square root of lambda. Right? I can go back and forth between those. And that's how I can get my my natural frequencies from my eigenvectors. And K is symmetric, so it's a symmetric eigenvalue problem. All right. Tell you a little story. How I once wasted 2 weeks of my life sitting in an office building off an Air Force base in Florida. So it's important, important attribute of eigenvectors and eigenvalues is that they encode only the information about the direction of the transform, and the magnitude is captured by the eigenvalues, right? So therefore, different values within an eigenvector can be used to represent the same direction, right? Or the same eigenvector. So you might have different eigenvectors that are actually absolutely the same. The challenge then for kind of entry, for practitioners or entry-level practitioners is that different software packages take eigenvectors differently. Your good friend MATLAB is designed for engineering folks, right? So MATLAB takes the 2 norm of each vector, so it normalizes the vector. It's a very good way to do it. Other older software, like something called LAPACK, which is part of the Intel suite and is an old Fortran thing, they don't normalize the vectors, the eigenvectors, right? Python, NumPy, I believe, normalizes the vectors, but SciPy doesn't. There's a few different ways, and this was a couple years ago when Python was rougher, and I ended up emailing the people who worked on NumPy to figure it out because the documentation was wrong. Anyways, from different software packages, you can get different eigenvectors that are exactly the same thing. And so if you try to mix and match eigenvectors and eigenvalues solved in different software packages, they won't match up at all. So just think about kind of what's coming out of your software package and be cognizant of the information that, again, that the eigenvectors are not, that are just a direction. Another thing is oftentimes software packages will organize it. So the lowest value of your eigenvalue is your first frequency, right? But not all software packages put them in smallest to highest. And so you would have to reorganize your eigenvalues, but then you have to reorganize your eigenvectors, right? And so just think about that as you're doing things. You kind of have to constantly go back and check. All right, so let's talk a little bit about normalizing vectors. The Euclidean norm of a vector. So this is kind of review 5.4. So yeah, sorry for that word salad, but keep an eye out for things that don't quite match. Euclidean norm of a vector, also the 2 norm of a vector is defined as my vector 2 norm is equal to my summation of n, summation of I equals 1 vi squared is equal to the square root of v transpose v. So if this 2 norm of v equals 1, it is a unit norm. If not, it can be converted to 1, right? So basically, to convert it to a unit norm, we just need to find alpha v equals 1. We just have to find some value for alpha to convert it to a unit norm. I think the easiest way to do it is just to go, you can go v normalized is equal to 1 over the square root of v transpose v. Right. All right. Example 5.3, we'll go over normalizing vectors. I know that's something that you've all done, but good to take a look at example 5.3. If needed. But the idea of a unit norm vector is pretty. Everyone heard of a unit norm vector? Done it once? Okay, yeah. Question.
So why bother normalizing it just so you can like compare apples to apples?
Yeah, you just want to, and you need it for mode shapes. Mode shapes normalize, right?
Aesthetically pleasing.
It's aesthetically pleasing. That's very important. Okay. All right. So from our eigenvalue solution, let's say omega I is equal to the square root of lambda I. So our natural frequency for the first mode is equal to the square root of our first eigenvalue. That works pretty well. Again, the eigenvalues are not the natural frequencies. They're just related to the natural frequencies. So the eigenvectors are 2. And we just have to put the mass back into the system, right? So u of I vector, because it's a mode-shaped vector, is equal to mass negative 1/2 v of I, or u1 v1, right? let's say you had the mode shapes. I don't know why you would want to. But let's say you had the mode shapes and you want your eigenvector, right? V eigenvector is equal to mass 1/2 U. Okay, those both of I. They are vectors. So you can go back and forth. So they're related through the mass normalization process.